Okay, in this video we're going to talk about it's kind of a hodgepodge little catch-all little lecture, but it's talking about trends within common elements. Okay, so we're actually going to look at the vertical columns for some of the common options here. The idea is the periodic table is organized so that things that are in the same column tend to have at least somewhat similar properties. I'm not saying they're identical, but you know, like copper, silver, and gold are all like soft metals that withstand heat and don't oxidize very nicely. The noble gases are all in one column, stuff like that. So what we're going to do is we're not going to talk about every column because there's a lot of elements. We're just going to look at some of the common ones. Okay, so group 1A. Basically, this is lithium, sodium, potassium, rubidium, cesium, gas francium. It's francium super radioactive and has a really unstable half-life. It doesn't last very long. These are known as the alkali metals. Okay. Some of the common trends between them, they are very soft metals. Okay. I've actually like sliced into a chunk of sodium with like the equivalent of like a butter knife, like a scupula in the lab. Like you can just take a piece of metal and just cut right through it. It doesn't have to be sharp at all. Okay. They tend to have very low densities. They're very lightweight metals. Okay. They have low melting points. It takes almost nothing. It takes minimal heating to make it a liquid. Okay. They are easily and rapidly corroded by oxygen. So if you had a chunk of sodium and you sliced into it, the outside would be all crusty and gross looking because it would look like the equivalent of rust for sodium. If you slice it, it's very easy to slice, and the inside is shiny. It looks like metal. It kind of looks like tin foil or aluminum foil. It looks like metal. Okay. But within seconds, it becomes corroded and gross again. It's kind of like if you visualize like iron, it rusts really slowly. It can rust eventually, but it's just iron reacting with oxygen. You end up with that brown, crusty rust stuff on the outside. These metals, it happens within seconds, no matter what. Okay. They also react violently with water. I'll see if I can post some videos of examples of these things exploding in water. Okay. Essentially what happens is, so let's look at sodium, stereotypical example, okay? What happens is you take sodium solid, react it with water, kind of just balancing as I go here, and it actually forms sodium hydroxide, which means the solution that you form at the end is actually very, very basic, alkaline, which is where that term comes from. But it also produces hydrogen gas. So this is super flammable. And this has a very negative delta H. So this produces a lot of heat and a gas that's flammable. So basically if you throw it in water, most of the time the gas as it starts spewing out catches on fire and it'll basically dance around the top of the water and flames will be shooting out. Sodium makes very distinct yellow flames. Potassium's like purple and orange flames at the same time. They each are pretty distinctive, but this is the general reaction, okay? So nothing really critically important here, but just kind of getting some general trends here so you at least heard of these things. Okay. Group 2A, okay, so the next column over, this is beryllium, magnesium, calcium, strontium, barium, and radium. Radium, again, is radioactive, so we don't really encounter that one a whole lot, but it's not uncommon, actually. Okay. These are known as the alkali earth metals. Okay. They're essentially like the tamed down version of these. These things are like ridiculously, any trend they have, they're like really far off the rails of what's normal. These are like the tamed down version. So they're harder, denser, and have a higher melting point. I'm going to abbreviate that as MP. than the alkali metals, but they're still soft, low density, and have low melting points. They're just higher than these values. Okay. They also corrode easily by oxygen. It's just slower. Not like a lot slower. They still corrode pretty easily, but compared to these, this you can literally watch it happen in seconds. This will take minutes. Okay. And they react with water and form alkali solutions, which is why they're called alkali earth metals, but they don't explode. They don't shoot flames out of the top. So they do react with water to form basic solutions. And it does produce hydrogen. It just produces it so slowly that typically the hydrogen will blow away before it has the chance to catch on fire. Okay, so not a huge deal, but these ones are pretty noteworthy for being able to explode, and these ones really aren't that much less reactive than this. They'll still do similar stuff. Okay. Unfortunately, the D block, there's hard trends to spot. We mentioned copper, silver, and gold. They're very soft metals. Very shiny metals. They don't corrode very easily. They're great, okay? They're good for jewelry, okay? Things like nickel, palladium, platinum are used a lot as catalysts, like in catalytic converters in your car. They're very, very stable metals. Yeah, I mean, a lot of times these metals in the middle actually end up getting mixed together to make alloys, so it's hard to spot one trend by itself. You can get like a chromium iron nickel alloy, and it has certain properties that aren't in nickel, iron, or chromium. So yeah. So let's look at the far end over here. Let's look at group 8. Let's kind of work from the other direction. Group 8A are the noble gases. So I guess I should write them all down. Helium, neon, argon, krypton, xenon, and radon. These are the noble gases. Okay. They basically are unreactive, is the easiest way to phrase it. They're usually described as inert. In other words, they don't do anything. There is one exception. Okay. It turns out that xenon can react with oxygen or fluorine under really harsh conditions. And honestly, these things hadn't been discovered until, like the past 50 years. So literally 50 years ago, nobody even knew this was an option. Okay. I guess the 1960s, sorry. But you can actually, there are compounds like ZeF4 and XeO2, like those are compounds that can exist now. But for the most part, these things don't get used for anything, except in labs. A lot of times, if you need a work area where you don't want any oxygen, like if you were going to work with sodium in its purest form, you could actually fill a chamber with something like argon or neon, and you could work in there and it wouldn't hurt you at all, but there wouldn't be any oxygen there to corrode it. So you could actually, we use it as like a filler gas to remove anything that might be reactive. Okay. I'm gonna probably run out of space, but I'll try it anyway. Group 7A, this is fluorine, chlorine, bromine, iodine, and astatine, which is super unstable and really uncommon, but I'm gonna put it on the list anyway. These ones all actually exist as diatomic molecules. Astatine, maybe not, we don't really know actually. It's one of those ones that it's really unstable, so it probably doesn't even have time to do that. But they don't exist by themselves. They exist as molecules of like two fluorines or two chlorines or two bromines. They exist like that. Okay. These are called the halogens. I've probably mentioned this in passing in class, but that's okay. They are very reactive. Okay. They really like to form negative charges. They're all one away from being a noble gas. So they will happily violently steal electrons from other atoms. Okay. As far as the trend, it's kind of hard to spot. Fluorine is a gas, chlorine is a gas, bromine is a liquid, and iodine is a solid. And astatine is probably a solid, but we really don't know because it's really uncommon. Honestly, I probably should just mark astatine out on my list. It's so uncommon, you don't really need to know anything about it. Okay. They are honestly very, very poisonous. Your body does not respond well to pure elements of this stuff. I've accidentally breathed in fumes of bromine before on accident when I was cleaning out a lab and one of the lids had busted off or something. And I want to say it kind of felt like getting hit in the lungs with a hammer. I've never been hit in the lungs with a hammer, but I would guess that that's what it felt like. I would recommend against. How about that? But we sometimes use this to our benefit. So like chlorine, we use to purify drinking water. We use it in swimming pools to kill anything that's growing in there. We use the poisonous attribute to help us. Okay. Fluorine, they actually use fluorides to like help strengthen enamel in your teeth. Yeah, stuff like that. Okay. All right. The last column that we're going to talk about is column 6A. This is just known as the oxygen group because it's the most noteworthy thing in that column. So this would be oxygen, which is also diatomic, sulfur, selenium, tellurium, and polonium, which is super radioactive and not real stable. Okay. Honestly, if you ever look up stuff about the oxygen group, it mostly talks about oxygen. So let's talk about oxygen for a second. Oxygen can exist as O2 or O3. O3 is, so oxygen is odorless, colorless, tasteless. You're breathing it in right now and you wouldn't even know that it's there. You'll notice when it's gone, but you can't tell that it's there. O3 is ozone, and it actually does have a smell to it. And your body doesn't like ozone a whole lot. It's kind of got this pungent odor. But these are like the two options for how oxygen can exist. Oxygen is really reactive. As far as the periodic table, there's only like a few of the noble gases are like the only thing on the periodic table that won't react with oxygen. Oxygen will react with damn near anything. Okay. It's also poisonous in excess. If you just try to breathe pure oxygen, like right now our atmosphere is about 20% oxygen, maybe. Kind of depends on the day and elevations and all that stuff. But if you actually try to breathe in 100% oxygen, your body freaks out and dies. It's also poisonous to anaerobic bacteria. Anaerobic means basically not in the presence of oxygen. But this is why if you were ever a kid and you skinned your knee, like you're running and you fell on the sidewalk and skinned your knee, the hydrogen peroxide gets put on the wound. It breaks down in the presence of water to produce oxygen, and the oxygen can kill any anaerobic bacteria so that your cells can recover quicker. Okay, so they're not fighting an infection. Okay, and it also just creates an excess of oxygen for even aerobic bacteria. It can only handle so much, so it helps minimize the risk of infection. Okay, so like moving down the list, sulfur is the next most likely thing to encounter. Selenium, tellurium, polonium are all pretty rare, so we're not going to really focus on those a whole lot. It is like the milder version of oxygen. It does react. It forms the same types of charges. It actually forms the same type of compounds. It's just not as violent about it. It'll form, but you're going to have to push it a little bit. Okay. It actually exists as S8. Okay. A lot of times we kind of cut corners, and when we're writing balanced equations, we just write it as an S, but technically it exists as S8. It exists as this alternating zigzag thing that forms a ring. I don't know how to draw that, but 1, 2, 3, 4, 5, 6, 7, 8. I don't know how to make that connect, whatever. Okay, it's a weird little molecule, actually. It's a common pollutant. In coal and fossil fuels. It's actually like burning of coal and fossil fuels that have sulfur in it is what leads to one of the primary sources of like acid rain, sulfuric acid forms. Honestly, its most noteworthy thing is that it smells terrible. If you've ever been, I doubt it, you guys all live in New York. If you've ever been out to Yellowstone National Park, they have geysers out there, and they all smell like rotten eggs. It's because there's a bunch of sulfur in there, and as this hot boiling water comes out, literally just you can smell when you're near a geyser. H2S is basically what makes rotten eggs smell like rotten eggs. It's also what makes geysers smell bad. So, this video was kind of a weird little random one, just like a catch-all thing that like may not have gotten covered in other stuff. Really fast, I also want to talk about, I've kind of mentioned a couple things that form like diatomic molecules. I want to make sure I've officially addressed what a diatomic molecule is. There are 7 of them. 7 elements that form diatomic molecules, and oddly enough, they form us 7 on the periodic table, and hydrogen. Hydrogen's the weird one. So it's H2, N2, O2, and then all the halogens. So F2, Cl2, Br2, and I2. Okay, there's nothing really worth, it's not like a huge deal, but if you're ever writing balanced equations and you need nitrogen in there, it doesn't exist as N, it exists as N2. If you're talking about chlorine, it exists as Cl2. But in terms of memorizing which ones, I remember this from high school. There are 7 of them, and they form the shape of a 7 on the periodic table, and then hydrogen. So, easy little mnemonic device. All right, thanks.